Okay, anybody have any homework questions? All right, so last time, the time before last, we're never talking about that again. Last time,
wait, you actually did well last time.
Last time was fine.
The time before that
was not good. Yeah, it didn't happen. No video, didn't happen. So we were on column buckling. And we did the case where you had pins at both ends. So the column was pinned there, attached to a pin at the top. And you apply a force like this. And we came up with this general solution that said the deflection as a function of x is equal to a times the cosine of p over ei. What's the name of p over ei? No, not p over ei, sorry. What's the name of ei? Flexural rigidity, good, yeah. Flexural rigidity. Yeah, it's hard to say fast. Plus b times the sine of square root of p over ei. That's your right? What homework? Rigidity. Tiggity. So we got this, and then when we solved it for the boundary conditions, we got that P for equilibrium is equal to EI. Well, in general, we have N squared, EI pi squared over L squared. And so if there are no restrictions along the length, then you get the critical p-value. N is equal to 1. You know, this is for any n value. So P critical is equal to E I pi squared over L squared. And then if there are restrictions, then P critical is for the n value that meets those restrictions. Okay, so that means that if you have restrictions along the length, the critical p-value goes up pretty quickly because that n is squared. And so the easiest, and it makes sense if you think about it physically, it's easiest to cause this to buckle if there's no restrictions, and then if you add restrictions to it, the load required to make it buckle goes up. So now we're going to deal with the case where the joint between the column and the ground is a fixed joint. And there are two cases that we're going to talk about, but you could use this approach for any kind of restrictions in addition to these. But the first one is where the angle is fixed at both ends. So the angle fixed at both ends. And then the other case, it's a fixed joint at the ground, but it's free at the top. And both of these, we're loading still in with a compressive force. You can't do a problem, well, don't ever design something with a column that is free at one end and a pin joint at the other end. That's not very stable. So this is the only case we're going to deal with, but this one is going to deform into a shape like this. And this one is going to deform into a shape like this. Those are exaggerated. Remember that in order to use the equations that we use, we require that v prime is close to 0 for the whole thing. So you can't have big changes in slope like that. But that's, a blown up kind of version of the shape. Okay, so first let's come up with a general solution, and then we'll go into the boundary conditions for each individual case. So we're going to find a general solution for a column that's fixed to the ground. And so I'll start with a free body diagram. It's not going all the way to the top, so it just starts out with the connection at the ground. And then, ooh, I almost drew it the wrong. Don't do it like this. No.
I'm starting to remember that day.
Yeah. No, didn't happen. Okay, so what kind of loads act? And we have the x-axis that way, y-axis that way. So there's a force P acting up there and a force P down there. And up here, there's the internal bending moment. That's all the same as it was before. But now, because there's a fixed joint between the column and the floor, there's also a reaction moment there. I'll call that M sub 0. And so rotational Newton's second law says that reaction moment M sub 0 plus the bending moment M plus this is the deflection V. And so that's a counterclockwise moment that's equal to P times V. And those have to, for this to be in equilibrium, those have to add up to 0. The elastic beam requirement is that M is equal to E I B double prime. So you can rewrite this as E I V double prime plus PV is equal to negative M sub 0. And then divide everything by EI, and you get the general differential equation that we're going to be working with. V double prime plus P over EI times V is equal to, and at this point, everything looks exactly the same as it did with the pin connection between the column and the ground. But now, instead of 0 on the right side, we have negative M sub 0 over EI. All right, well, last time, we used the fact that if you have something double prime plus some constant times that dependent variable equal to 0, you have a solution that's equal to a constant times a cosine plus a constant times a sine. Now we don't have a 0 on the right side. So the way that we're going to deal with this is, okay, so now there's a constant on the right side of our differential equation. So to find a general solution for this, we're going to have, so we're going to set it up like this. The general solution, V of x, is equal to a general homogeneous solution, V of x, and I'll say what all these mean, plus not a general, just a particular solution, Vp of x. So where V sub h of x is a general solution to the homogeneous equation, and with a differential equation, the homogeneous equation is where you take any terms that are not proportional to the dependent variable and set it equal to 0. So in this case, this term, the double prime, that's the dependent variable double prime, so that stays. This one is multiplied by the dependent variable, so that stays. But this one that's just a constant, we set that equal to 0. And in general, when you talk about homogeneous solutions, this could also be a function of the independent variable, and it still would be set to 0. So this could be, negative m sub 0 over EI times x or times x squared or whatever. As long as the dependent variable v doesn't appear, for the homogeneous case, we set that equal to 0. So the homogeneous equation says p double prime plus p over EI times v is equal to 0. And here we need to find the general solution. We need a representation of every possible solution of the homogeneous equation. But then the particular solution, we just need to find one. We don't have to come up with a general form. So that particular solution, v sub p of x, is any single solution to a full equation. And that full equation is V double prime plus P over EI times V is equal to negative M sub 0 over EI. Okay, so we need a general solution to the simpler equation, the homogeneous equation, any single solution to the more complicated equation, and then we just add them together, and that's a general solution for the constant case. Okay, so that's the strategy. So first, we need the general solution to the homogeneous equation. And that's the case that we've already done before. This is the equation that we solved for the case of a pin connection. And so that general homogeneous solution, V sub h of x, is a times the cosine of the square root of p over ei times x. And this is all an argument to that cosine, plus b times the sine of the quantity p over ei times x. Okay, that was easy. And now we need any single solution to the full equation. Well, notice that if we can come up with a single constant solution to this equation, a single constant expression v that solves this, all we have to do is come up with a case where this is equal to that, because if v is equal to a constant, you take the second derivative of it and it goes away, And so that's what we're going to do. We're just going to come up with an expression for v that's a constant that satisfies this equal to this. Then the second derivative of v is 0 and the whole thing is satisfied. Okay, so we're going to make our v particular a constant, and vp double prime is equal to 0. So all we have to do for this is meet the requirement that p over ei times this constant vp, so p over ei times vp is equal to the right side of the equation. That's negative m sub 0 over ei. Is that what it was? Yeah. Now solve for v sub p. You can cancel these. And v sub p is equal to negative m sub 0 over p. And that constant solves the full equation. It's not a general solution. Obviously, a constant doesn't give you every possible solution there. But if you take that constant and take the second derivative, it's equal to 0 plus p over ei times that constant, it gives you that. So it solves the equation. But do you have any questions or want me to clarify anything on that? For the people who are in dynamics, we're going to use that same idea when we talk about forced oscillations. And it's a forced, yes. And it's a useful approach for differential equations in general, ordinary differential equations and partial differential equations. If you have a non-homogeneous differential equation, you can get the general solution by finding the general solution to the homogeneous and adding it to any one particular solution. Okay. So our final answer for V as a function of x is A times the cosine of the quantity P over EI square root times x plus B times the sine of the quantity root P over EI times x plus the particular solution, so minus m sub 0 over P. This together is our homogeneous solution. This is our particular solution. And overall, this is the general solution for a fixed joint with the ground. And now that we have that general solution, now we're going to use the boundary conditions for each specific case. So we use the boundary conditions for the specific setup to find the critical p-value. So the first case is the case where the angle is fixed at both ends. And then the second case is where it's fixed at the ground, but free. Okay, so start with case one. This is where the angle is fixed at the top and the bottom. And the boundary conditions in this case are, first, we know that there's no deflection at the ground. It's fixed, so it can't move around. So at x equals 0, v is equal to 0. Second, because it's a joint, not a pin joint, we also know that at x equals 0, v prime is equal to 0. That's the angle being fixed. And then the third one is, because this is symmetric, we know that exactly halfway along the beam, the slope of that beam, v prime, has to be equal to 0. So here's to visualize it. We're talking about there's a symmetry along this line, and that means that the slope v prime right at that point has to be 0. There can be a deflection, but the slope has to be 0. Okay, that's required for that symmetry. So that last restriction says at x equals L over 2, v prime is equal to 0. Okay, so the first one, the first boundary condition, our v is equal to a times the cosine of the stuff in the square root times x plus b times the sine of the stuff in the square root times x minus m sub 0 over p. At x equals 0, this says a times cosine of 0 is 1. Sine of 0 is 0, so this term goes away, and we just have a minus m sub 0 over p is equal to 0. And so a is equal to m sub 0. And so now update the function. Just one by one, we're going to go through these boundary conditions and keep updating that function. So now v of x is equal to m sub 0 over p times the cosine of square root of p over ei times x plus, we still don't know what b is, times sine of square root of p over ei times x minus m sub 0 over p. And now we'll go to the second case, or not the second case, the second boundary condition. Please stop me if you have any questions about any of these. So now we're using the boundary condition that says at x equals 0, v prime is equal to 0. V prime is equal to negative m sub 0 over p times the square root thing times sine of the square root thing times x. The derivative of the second term with respect to x is b times the square root thing times cosine of the square root thing times x. And derivative of the constant with respect to x is 0. So now plug in x equals 0. And that first term goes away, and now you have, so the first term goes away. The second term, the cosine of 0 is 1. So now you just have that b times the square root of p over ei is equal to 0. So b has to be equal to 0. And so now we can update this again. We have now that v of x is equal to m sub 0 over p times the cosine of square root of p over ei times x minus m sub 0 over p. And I'm going to rearrange that into pull out the m sub 0 over p, and that times cosine of the square root of p over ei times x minus 1. Okay. So now we know what all the constants are. Now we want to use the last boundary condition to find that critical p-value. And so the third boundary condition says at L over 2, at x equals L over 2, the slope has to be 0. So V prime is equal to negative m sub 0 over p times the square root of p over ei times the sine of square root of p over ei times L over 2, and that has to be equal to 0. This only occurs when the argument to that sine is equal to n times pi. So we have square root of p over ei times L over 2 equal to n pi for n equals 1, 2, 3, and so on. Square both sides, and you get p over ei times L squared over 4 is equal to n squared pi squared for n equals 1, 2, 3. Keep going up. And at n equals 1, we get the critical p-value that's equal to 4 ei times pi squared divided by L squared. If you have any restrictions along the length of the beam, then you choose the n value that meets those restrictions. So how does this critical p-value compare to the critical p-value for, say, the same beam but pinned at both ends? 4 times bigger, yeah. So those restrictions of the angles at the end mean that that beam can support a lot more compressive force. And we'll do an example of that next time. Anybody have any questions right now? Okay.